Hi everyone, I'm Niranjan Vijay and I'm going to present about my ECE 591 project, Reinforcement Learning Based Voltage Support for Microgrid using Energy Storage System. This is the general outline of my presentation. First, I will talk about the background and then related work and objective, basic of reinforcement learning, subtractor critic algorithm, simulation setup, result, and conclusion. So, in the conventional power system, most of the generation are generator based. Could be hydro generator or diesel generator, but the amount of renewables is very small. These generators are bulk in size but fewer in numbers. So the simple mathematical model would be sufficient, and model-based control is uh, and model-based control performs pretty good. However, in the microgrid, the generations are mostly inverter-based. These these generations are smaller in size but large in number. So the simple model might not be very accurate, and the model-based control might not perform better in microgrid. Also, the R by X ratio, which is the resistance by reactance of the line, it is large. So the voltage would be more sensitive to the active power, and the voltage dynamics would be very fast. The active power is associated with the actual energy, so the cost of active power is higher, and the reactive power, it just requires the inverter operating, so the cost of the reactive power is lower. So the voltage support technique is required that can incorporate both types of power, active and reactive, as control input and is model free. That is, it doesn't require the mathematical model of the microgrid. These are some of the related works about the voltage support for microgrid. So the model based approach has also been proposed in the literature, but like I mentioned before, it requires the prediction model of the microgrid. So the different type of reinforcement learning based approach has been proposed. However, all this work focuses on the steady state voltage profile only. None of the work focuses on the dynamic voltage support. So the objective of this project is to develop model-free reinforcement learning-based voltage support technique for microgrid. The reinforcement learning is basically the training of model to make a sequence of decision. So in reinforcement learning, we have some environment where the agent takes some action and receive the reward, and the environment go to the next state. The agent is the machine learning model, and there is a term called policy, which is basically the mapping of this state to action. So the reinforcement learning policy can be divided into two class: on policy and off policy. So in on policy that we want to update should be same as the policy used to collect the experience. That is, if if I update the policy, then the old experience cannot be used to update, because the now after updating it, the policy has changed. In off policy algorithm, the policy to update and the policy to collect experience does not need to be same. We can use the old experience from the replay buffer as well. So the advantage of on policy would be the training would be more stable. Like the training is very similar to the supervised learning, and it is less sensitive to hyperparameters. The advantage of the off policy is it is sample efficient because we can use the old experience as well. And the disadvantage of the on policy is sample inefficient, and the off policy is sometimes the training might be unstable if we use it like a different value of the hyperparameters. The example of on policy is TRPO and PPO and A to C. And for off policy, the examples are DQN, DDPG, TD3, soft actor critic. So now let's talk about the actor critic method. So as we studied earlier in DQN, uh, we can find the optimal action by comparing the Q value for all the action, and the and the and the action corresponding to the maximum Q value would be the my optimal action. So what if my action space is continuous? We cannot use the same technique now, because the possible value x the number of possible value of action are infinite in number. So in this case, a separate network is used which gives the A for a given value of x, for a given value of s, the state that maximizes the Q. This separate network is called actor. The actor, as shown in figure, it calculates the action which is applied to the system, and the system moves to next state, and the agent receives the reward. So based on the reward and the state it went to, it gives the Q value, which is basically the expected reward of the future. So this Q value determines how to update the actor. Q value is like a feedback signal or for the actor. So in a nutshell, critic criticizes the action taken by the actor, and this is how the actor critic network works. Let's go to soft actor critic method. In soft actor critic, we have one actor and two critic networks. So the two critic networks are used to minimize the overestimation of the Q value. And also the target network are used similar to the DQN. And the objective is to maximize the Q along with the entropy with some suitable trade-off. So these are the key equations used in the soft actor critic. The first equation says how to calculate the state value function from Q function and the policy. The second equation is the loss function for the critic network. This directly comes from the Bellman equation. Bellman equation says this and this should be equal. So what is being done here is the error between them is being minimized. The third equation is the loss function for the policy. So we want to maximize the Q, so the loss would be just a negative of the Q. When we minimize this part because of a negative sign, we would be actually maximizing the Q. And this log of probability is the negative of the entropy. So we are minimizing the negative of the entropy, which means we are maximizing the entropy with some coefficient alpha, where alpha is like a trade-off factor. It is also called entropy coefficient. And the last equation says loss function for tuning the alpha. The alpha should be chosen such that the entropy of the policy is same as the target policy, which which we have to define. And if you look at the loss function of the policy, the action, it is sampled from the policy, and the not only just the value of action is used here. We have to use the reparameterization trick to sample it. We will explain the reparameterization trick in the following slide. And this is the overall soft actor critic algorithm. So initially, we define the trainable parameter of the neural network, and then we create the target network. And the parameter of the target network are represented respectively by by a bar on its original main network parameter. And this D is the replay buffer. So it is initialized empty at first. So for each iteration, we have to sample the action from the policy and then apply the action to the environment. Now the environment, which is at the state EST, moves to state EST plus 1, and agent receives some reward. So this tuple is stored in the replay buffer. And to update, we sample the data from this replay buffer, and then we calculate the corresponding loss and perform the gradient descent or back propagation to update the neural network parameter. And finally, the soft update of the target network is performed. Let's talk about the reparameterization trick. So the actor network, it doesn't directly gives the value of the action. So in soft actor critic, the policy is stochastic, which means the action is some random variable following some distribution. For continuous action space, normal distribution is assumed. And the actor network gives the parameter for the distribution. Like since it is a normal distribution, the parameter would be mean and the standard deviation. But the network, it gives the log of standard deviation. The reason for choosing log of standard deviation is this standard deviation is always should always be positive. It cannot be negative or zero. So if neural network outputs the log of standard deviation, then even if this part goes to negative or positive, it doesn't matter. The sigma would always be positive. So the value of the mu and the log sigma is passed to the sampler, which samples from the normal distribution of mean of mu and sigma, yeah, of this. And the sampled output is passed to the tan-h function. This tan-h function, it limits the output from -1 to the +1, which can be scaled to the range of minimum action to the maximum action. And this action will be supplied to the environment. Now, during the update phase, we sample the state from the replay buffer, and then the action is sampled from the policy, and then a loss function is calculated, and then it is back propagated to update the neural network parameter. So the back propagation through this part scalar is straightforward. Scalar is just the multiplying with some constant gain, so there is no problem in back propagating through the scalar. And from the tan h, it is also no problem because the derivative of the tan h exists, so there is no problem. The problem is in this sampler. The sampling, this sampler is the output, like this, the output of the sampler is not some like a defined function of mu and log sigma. So how do we back propagate through this sampler? In other words, if y follows a normal distribution with mean mu and variance sigma square, how to find the derivative of y with respect to mu and derivative of y with respect to sigma? There is no direct way if we use this way, but if we sample use another way, we can write the this y as mu plus sigma times epsilon, where epsilon is sampled from normal distribution of mean 0 and variance 1. These and this are equivalent. However, from this case, we can calculate the derivative with respect to mu and sigma. So this technique is called reparameterization trick. So with this, we can backpropagate through the sampler, and then we can backpropagate through the neural network to its trainable parameter and update the neural network. So there is a package called TensorFlow probability that already takes care of this reparameterization trick. So if we implement this sampler using TensorFlow probability package, then we shouldn't have to worry about implementing this thing. Now let's talk about state space in VoltageSupport. To implement the reinforcement learning algorithm for any environment, we have to define the state space. So in video game, what would be the state space? Is it the current frame or the sequence of frame? So we have to be careful whether my state space current sufficient information to make a decision. If you just take the current frame, then the information about the movement of the character would be lost. We wouldn't know whether the character are moving or just is standing still, or even if it is moving, how fast it is moving, in which direction it is moving. We would lose those information. But if you use the sequence of frame, then the agent might be able to extract those information. So in general, this structure of neural network is used. There's an observation which is large dimensional. Then we implement a feature extractor layer that reduces the dimension of the observation to smaller dimension. The nature of this feature extractor should be chosen based on the type of observation we are using. If it is image, then it could be CNN. If it is time series data, then it could be recurrent neural network. So this feature, the output of the feature extractor, which is the feature, is passed to fully connected network to get the to implement the actor network or the critic network. So for the voltage support, we have a microgrid where we only have the local measurements available. So microgrid can have large number of nodes, but the measurement from all those nodes are not available. So what is going on those nodes are completely hidden from our is completely hidden to the agent. We can only use the locally available measurement. So instead of passing the measurement from just the current time, we have to pass the sequence of available measurement of defined sequence length L. So from the data of the sequence length and how those measurement are changing with time, the agent would be able to extract a useful feature, which can and the agent can make a better decision. So the state space, yeah, for the voltage support would be like it would be time series data. So the simulation setup. For this project, I have used very small microgrid. So there is only one generator, one PV, which is connected to the transformer, and we have a load here. So there is a base load of PL which is connected all the time, and we made a load change of delta PL. So because of this load change, the voltage deviation occurs. So the objective here is to minimize that voltage deviation. So since the value of PL and delta PL could be anything, we know its range, but we cannot know what would be its actual value because this information is not available to the agent. We can only use the measurement from this node. So what we have to do is, for each episode, we have to sample the value of the PL from this range because this is the general range of the load, and the delta PL could be anything. So we sampled delta PL from this range minus 0.2 to plus 0.2. Plus 0.2 means adding the load, and minus and the negative value of the delta PL means we remove some load. And this is the general range of load change. And we have set the target entropy of the -2 because the original soft actor critic paper suggests the target entropy of negative of dimension of the action space. So in this case, the dimension of the action space is 2, D and Q component of the inverter current. So the target entropy is set to -2. And the reward function. So this is the reward function I have used in this work. So the reward function, the agent tries to maximize this reward. So here is the minus sign in front, so which means agent is actually trying to minimize this part. Minimizing this part means minimizing this part as well as this part. So let's talk about the first term. This term represents how much is the voltage deviation from its reference value. So this is basically our objective. So if the agent minimize this part, which means the voltage deviation would be minimized. And similarly, minimizing this part means the agent have to complete its objective utilizing smallest amount of inverter current as possible. And the structure of the neural network. So as I already mentioned, the state space in the voltage support would be time series data. So in that case, recurrent neural network would be the feature extractor. So I have used the LSTM network of sequence length 25, and the output of the recurrent neural network or the LSTM has the dimension of 10, and and two dense layer of size 64 are used with ReLU activation function, and finally the output layer has the dimension of 2 with linear activation function. Critic network is similar except the output layer where the dimension is just 1. And after performing the training, this is the how the different training metrics changes as the training proceeds. So the first one is the mean episodic reward. Initially, the reward is very low because the agent is not trained, so it just takes a random action. As the training moves forward, the reward increases. So at first we see a lot of improvement, and then it takes a lot of time to make very small improvement. The second graph shows the entropy. So we set the target entropy to -2. So the actual entropy should also be close to the -2 as tuned by the alpha parameter. As seen from this plot, we can see that the entropy is actually very close to the -2. And the third graph shows the standard deviation for D and Q component. Here we can see that D component has lower standard deviation than Q component. It is because voltage is sensitive to the D component, which is the active power, than Q component. So the agent can easily learn the effect of D component on the voltage than the effect of Q component. So the agent is more confident about the um, um, confident about the effect of D component, and hence the standard deviation is lower. And this is the performance of the voltage support. So the first and the second graph, it shows the D component of current and the voltage. And from here we can see that the oscillation in both the voltage and current is reduced. And from the second graph, we can see that the voltage deviation is also reduced, which is our objective. And from the third graph, we can see that the higher magnitude of the Q component, which is the reactive power, is utilized as compared to the active power. It is because we set the value of R11 higher than R22, which means um, the agent gives more priority to minimize the D component as compared to the Q component. So in the conclusion, we can say that a reinforcement learning based voltage support technique is developed, and which does not require the mathematical model of the microgrid. And the agent is performing pretty well in the smaller microgrid, which has been used as a test system. So in the future, um, I will test this technique in the large microgrid model. And this is the reference. Thank you.